So first stop on the journey is electronic trading and microburst analytics. My name is Ron Evo. I'm the CTO of cPacket. We're talking roughly around circa 2012. This is when we started doing things. And if you remember the chart of all the products, we're really going to talk about our what we call packet brokering, packet delivery, and the centralized command and control. Before we go into the solution and how we do that, I think it's worth, for those that are not familiar with electronic trading and how it works, to spend a little bit time to understand the ecosystem of electronic trading. So electronic trading is all about the stock exchanges, the equity exchanges, the foreign currency exchanges, unlike phone exchanges. And this is where they get the orders to buy and sell. This is where the decision is being made. And in order for the traders to know how to buy and how to sell, they're sending all this data downstream, essentially on IP multicast network. So think about it as each trader on the right-hand side of the slide, left-hand side, is registering for a specific stream that carries specific tickers, specific movements, the tickers that they care about, and they will get the information, then they will make the decision to buy or sell based on this information. There is no retransmissions. Either you get the packet or you don't get the packet. And when you have an algorithm that has to do that, if they miss any single packet, they may get to the wrong decision. So someone told me sometime, these networks are critical. It's not about humans. It's not about lives. It's about money. So you can't screw up anything, right? You can't do anything bad. So it has to work. Now, the other challenge that they have is that it has to be ultra low latency, right? So you are not allowed to lose packets, and it has to be ultra low latency. And I'm sure, as we all understand, that means that you can have big buffers. That means that you'll have a buffer overrun pretty quickly. So that translates to microburst. Now, when we say microburst, many times people are, well, what does it mean, right? What does microburst mean? And what's wrong with the measurements that we have today? So to give some notion of why microbursts matter or what it means is, think about the internet, Ethernet starting in the 1980, 10 megabits per second. It took me 8 seconds to send a 10 megabyte file. Now it takes, on 100 gigabits per second, 0.2 millisecond, right? 3 orders of magnitude faster. A typical switch took a few seconds. If they're 1980, we didn't really have switches, but if you think about the router, that's what it happened. Today, on a low latency switch in the environment that electronic traders are working, it's about 3 milliseconds. All right? So what does it mean for us? So if you think about the network, or you look at the network and you see what we have there on the top, well, we're talking about the switch, right, that has 2 ports coming in, 1 port coming out, to make it very simple. And we mentioned the buffer can hold about 3.5 milliseconds. So we're looking on a single second, so 1,000 milliseconds. And you can see that in the graph, during that second, there was only less than 10 milliseconds of actual traffic. What does it mean? So I had 2 ports, and you can see in the graph on the right-hand side, we zoomed in into this burst, and we can see that there were 2 ports. Each one of them sent data for 5 milliseconds at 60 gigabits per second. Right? So the total amount of data that they sent, each one of them was 300 megabits. Right? Total data, 600 megabits per second. So if I'm thinking about, okay, what was the throughput during that second? It's going to be 0.6 gigabits per second. So I have a 100 gigabits per second port running at 0.6 gigabits per second. But then packet drops. That makes no sense, right? So I talk to people and they say, when we talk about bursts, and they say, we run our switches at 20% utilization, so we're good. Technically, you can have min to max 1,000 times faster, right? Because you have 1,000 milliseconds. So 20% means nothing. In this case, what you can see is that we only had about 4 milliseconds that they were running, both of them at 60 gigabits per second. There is incast. They are both trying to go to the same port. So you're running at 120 gigabits per second for 4 milliseconds, and you're going to get a packet drop. Packet drops, in the case of electronic trading, bad things will happen. Enterprise, something else will happen. But certainly, in the electronic case, they do care about this single packet drop. Make sense? Another way to think about the microburst, someone was talking about drinking milk in 10 seconds, if you know the Joy movie that was. So, if the baby was just doing it a little slower, everything would have been fine, right? It just couldn't wait. So that's another way to think about microburst. So it's nothing different, right? It's essentially buffer overrun that we've always known. It's just that when people look at the number and don't understand why it happened, it becomes a magic word, and people say microburst. But there is nothing new there. Make sense? Okay. To understand the problem, I hope. What are you going to do about it? So one of the things that happened, and again, cPacket, we can talk about the story exactly how we got there. But at the end of the day, as Mark mentioned, we actually came from the security, but we ended up essentially reimagining the packet broker. So packet brokers showed up around circa, again, 2010. And the challenge that we're trying to solve is the ability to take a lot of data into tools that couldn't scale up because of Moore's law was behind Gilder law, right? The network were running faster, and now we even have a bigger problem. And they had these, okay, we can use a switch, but if we need to do anything smart, we'll have this CPU around and we'll take the data, get into CPU, send it back, generates a new bottleneck, generate inaccuracies, a lot of things can happen, where cPacket essentially said, okay, what we have is the ability to take the CPU and completely distribute it, right? Because our ASIC is programmable for the specific use cases that we need. We took the ASIC, attached it to an FPGA, and put it on every single port. So the traffic never touches the CPU, right? Traffic goes straight from the port to the FPGA, another FPGA, so we can do things on the ingress and the egress. And we can perform all these functionalities that we're showing here, which include timestamping, inaccuracy of nanoseconds. We don't only detect the burst, we analyze the burst, and I'll show in a second what does it mean to analyze the burst. Essentially, what is the cause of the burst? And then we do a lot of things that are relevant when we feed tools. So we can filter data, we can say this goes here, this goes there, decapsulate. So as you start building a product and running it in an environment that requires packet brokering functionality, there is a lot of capabilities that we have there, probably in another session. Okay, but all that, the important thing is that all of that is done at the port, in every port, and I can do it either on ingress or egress. Before I jump to the demo, I just want to recap kind of how the things is working, because I'm going to actually not. So if you think about it, we have the products that are the capture and the packet brokering. They can run anywhere. They all have REST APIs, and they're all being reported to cClear, which is the centralized command and control and visualization we have. So the demo itself, I'm actually going to show cClear, the centralized command. Because even if you distribute all the functionality, at the end of the day, what you want to have is the user is going to log into one place, and this is where you're going to sit. So real quick, what I'm showing you here is cClear. It's running in our network on cPacket. So I'm sure we're going to have some surprises as we roll through the demo. You can see that it manages multiple packet brokers. I can see the packet brokers here as a summary. I can go in and see every single port and what it's doing. I can do all the configuration and management that you would expect from a centralized manager, including all the authentication, making sure that things are time synchronized. And essentially, it's letting both the administrator and then in a second we'll show you the user to operate from just one location. Even though they may have, and we have customers with hundreds of these devices, each one of these devices, and you have an example here, each one of these devices have up to 32 ports, or 32 ports. Okay.
Hey, Ron, this is Remington. All of the functionality that you can do from that UI, is that also available and configurable through API with the cClear?
Yes.
And/or CLI or some other methodology?
Yeah, every operation this is how cClear came to be, or the centralized command. It leverages all REST APIs. So we don't really encourage CLIs as such. The packet brokers do have them, but for the most part, we expect people to do things with REST APIs.
Cool.
So provide scripting if they want to do it on their own. Typically, they will do it through cClear.
Just to follow up on Remington's question, this is Michael Winston. Do you publish the data model for the backend information that's available via API?
Absolutely.
Sometimes the API can be complex and hard to know which table or where to pull information from.
Yeah, every device we have, you can come in here and ask for the API documentation, and we'll give you a Swagger file that you can download and automate. The data itself, the metrics themselves are being collected into, we're using today InfluxDB under the hood, and we publish the schema. So if you want the access to the raw metrics, you just have the schema of InfluxDB, and it's open. Yeah, so actually I should have. The whole idea is to integrate into corporate dashboards, right? So, we're perfect, we're doing very well in packets. We do acknowledge that you need some other tools, and many of our customers have a much bigger observability framework. So this is how they get access to our data, right? So these corporate dashboards, corporate databases, they either use the REST APIs, and if the only thing they care about is the other metrics, then they can just go there.
Hey, Ron. The metrics also show the failover, or is there a place to see failover or any port issues?
Yeah. So we support all everything you'd expect from the enterprise, so SNMP, syslog, all the normal management operations. Yep.
Hey, Ron. Andy Laptev, are you going to touch on use cases that aren't high-frequency trading subject to microburst? I'm trying to put this in a context of environments I've managed. All right.
We will.
Thanks.
Sorry. So we were in the CVNG. Okay. So what we're seeing here is the, just again, one random port. So I'm seeing now the metrics from one port in our environment over the last 24 hours. I hope it comes through. But what you're seeing there is one port, 24 hours. By the way, we're using Grafana on top of InfluxDB. So basically we said there is no reason to innovate around dashboards. There are many companies that do that. So, and I'm looking at 1 second resolution. So all of our devices report every second the metrics that they see. So 1 second resolution, essentially, if you compare it to the example I gave before, this is going to say 0.6 gigabits per second, right? But when I add the max, which is 1 millisecond, so we break the second into 1,000 milliseconds. We measure the throughput in each one of them, and we put what was the worst case. You can see that around midnight, even though there was nothing on the average that indicated that, we are actually getting pretty close to saturating that link, right? Actually, if I go even deeper, I can see that it's actually saturating the link. And the other interesting thing is that this thing is actually happening, if I'm looking over the last 2 days, every midnight, right? So this is great in the sense that, well, okay, I can detect a microburst, right? This is pretty good. But then, okay, what do I do about it, right? Who created this microburst, right? It's a port, it's monitoring our lab. There are quite a few devices there. And if you come down, you can see, yeah, there are quite a lot of devices over there. a lot of workloads that are running. So what you can do is zoom in and say, okay, now I understand who it was. So it happened to be some of our random engineering VMs. So there is a VM guy. Someone is running something on one of their VMs and creates this burst. So now I know the source of the burst. And not only that, I can also tell you within the second how big the burst was.
Yeah, Jeremy Schulman. So does your system automatically detect these microbursts and just say, hey, there's a microburst and it happened on this? Or does somebody actually have to have eyeballs on dashboards?
Okay, to create an alert, so we detect as in we report the number, right? What the impact is, you can set an alert and get the notification. We can alert in real time from the CVU, or you can use this to alert. We also monitor things if, like in market data, did you have a gap, which is actual impact, so we can alert on that, right? So not every microburst will translate to packet loss. So you can alert on one or the other.
Does the system come pre-configured to do that, or does the user have to set up all these alerts on their own?
The user will have to configure that. In this environment, when we talk about AI, this is where we try and be smarter. So in this context, what we're showing here, you'll have to configure it. Yeah, you'll have to decide.
Hey, Ron, this is Remington again. So you have labeled out random engineering VM. Can you clarify how that tag or label, or how the system has identified that this is random engineering VM?
Yeah, so we can use a set of IPs, IP ranges, set of VLANs, layer 2. So that we have a pretty flexible layer 3 to 4 ability to indicate what each workload is.
Okay, and so is the system like consuming IPAM information from like a
We don't consume it today automatically. We ask for someone to upload a spreadsheet.
I gotcha. Okay. And so then you load it in and the system is aware, hey, this is what this is supposed to look like. Okay.
Yeah.